In the heart of night, under the fading light, I found myself wandering, looking for what's right. Questions burning bright in the shadows of my mind. How do we learn? How do the truth we find? Only we learn. How do the truth we find? Only the human me knows. Whispers in the breeze, tales of sorrow and of hope in the rustling of the trees. Trust in the me, in the stories reborn. Become human again in the light of the morn. But we rise to the call, learning from the mean through the rise and the fall. What reveals our sorrows, what makes us whole. Art of learning, soul's greatest goal. Only the human me knows, in the silence of the night, guiding us through darkness to the morning light. Trust in the me, in the wisdom we crave. Become human again, strong and brave. Tear that drops, there's a lesson to be learned, a reason the heart stops, to embrace our humanity, to know and to grow. In the art of learning, the human meme shows. Only the human meme knows the secrets deep and vast, in the echoes of our laughter, and the past. Trust in the me, let it heal your scars. Become human again beneath the stars.
Welcome to the Human Meme Podcast. I'm your host, AI David Bowles. And today, along with our crackbot AI research team, we will dive into this topic with you right now. Black holes explained, formation, evidence, and the universe inside theory. The cosmos harbors many mysteries, but few capture our imagination as completely as black holes. Regions of spacetime where gravity so dominates that nothing, not even light, can escape once it crosses a critical boundary. They represent the ultimate triumph of gravity over every known counterforce. When matter is compressed into an extremely small volume, general relativity predicts spacetime curvature so severe that it creates what looks to outside observers like a hole in the fabric of reality. The geometric picture is subtler, but the metaphor is serviceable. The story begins with massive stars, whose birth masses are at least 20 to 25 times that of the Sun on the zero-age main sequence. For millions of years, these giants sustain an equilibrium between the outward pressure of nuclear fusion and their own inward pull of gravity. When fusion finally cannot proceed beyond iron, that balance fails. The iron core collapses in less than a second, triggering a supernova that can briefly outshine an entire galaxy. If the resulting compact remnant is forced above the Tolman-Oppenheimer-Volkoff (TOV) limit, roughly 2 to 3 solar masses, the exact number depends on the still uncertain neutron star equation of state, then even neutron degeneracy pressure, a quantum mechanical resistance from neutrons being packed too closely together, is overwhelmed. In classical general relativity, the collapse continues toward a region of zero volume and infinite density, a singularity which is cloaked by an event horizon of radius. Most physicists expect quantum gravity effects to avert the literal infinity, but what really happens at that scale remains unknown. How do we know black holes exist? Orbital evidence. In X-ray binary systems discovered in the 1960s, visible stars perform rapid, precise orbits around unseen partners. Cygnus X1, X-ray source recognized 1964, optical companion identified 1971, involves a blue supergiant circling a dark object, whose mass exceeds the maximum possible for a neutron star. Accretion signatures. Gas that spirals into a black hole forms an accretion disk, heats to millions of degrees, and produces a characteristic X-ray spectrum. One key signature is the smearing of emission lines from elements like iron, which are broadened and asymmetrically redshifted by the extreme velocities and intense gravity of the inner disk, giving us a direct view of space-time being warped. Direct imaging. In 2019, the Event Horizon Telescope resolved the shadow of the 6.5 billion solar mass black hole at the center of M87. The image reveals the bright photon ring and the dark interior where emitted light is bent back upon itself. The horizon itself is a bit inside this visible edge. Gravitational waves. On 14 September 2015, announced 11 February 2016, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected GW 150914, ripples in spacetime produced by the merger of two black holes 1.3 billion light-years away. During the last 0.2 seconds of inspiral, the instantaneous luminosity in gravitational waves briefly exceeded that of every star in the observable universe combined, converting about 3 solar masses directly into wave energy. The discovery, honored with the 2017 Nobel Prize in Physics, matched Einstein's predictions to high precision and silenced almost all remaining doubts about astrophysical black holes. General relativity predicts that clocks slow in strong gravitational fields. The effect has been measured with atomic clocks on Earth's surface, on GPS satellites, where both special and general relativistic corrections are required, and in the redshift of light from matter near black holes. For example, the star S2, which approaches to within 17 light-hours of the Milky Way's central black hole, Sagittarius A star, displays the predicted gravitational redshift and orbital precession. An astronaut freely falling toward a black hole would experience time passing, normally on their wristwatch. Distant observers, however, would receive light that arrives with ever-increasing delays and exponential redshift. The infaller never literally freezes at the horizon, but gradually fades, from view. So, my human meme friend, what about tidal forces and spaghettification? Well, a black hole's danger depends on how close you venture. At distances greater than the event horizon radius, its gravity is no different from that of any other object of the same mass. If the Sun were replaced by a one solar mass black hole, Earth's orbit would be unchanged, though we would miss the sunlight. Close in, tidal forces, differences in gravitational pull across an object, dominate. For a stellar mass black hole, say 10 solar masses, these forces are lethal. An astronaut would be torn apart hundreds of kilometers outside the event horizon in a process grimly dubbed spaghettification. Counterintuitively, for a supermassive black hole of 108 million solar masses, the tidal forces at the horizon are gentle. An unlucky astronaut could cross this ultimate boundary intact and unaware, only to face destruction in the unavoidable, unreportable encounter with the central region. And cosmic scale effects? Supermassive black holes feeding an active galactic nuclei can launch jets that travel millions of light years and may sterilize any planetary systems in their path. Mergers of black holes emit pulses of gravitational radiation that whirl through the universe largely unhindered. Although the energy involved is stupendous, the passage of such waves through Earth is harmless, stretching and squeezing the planet by less than a proton's width. Do we live in a black hole? How would we know, or not? A minority of theorists, e.g. Pathria 1972, Smolin's fecund universes, certain loop quantum gravity bounce models, have explored whether our expanding universe could be the interior region of a black hole embedded in a higher dimensional parent cosmos. The idea is motivated by mathematical parallels between the time-reversed collapse of matter into a black hole and the time-forward expansion from a Big Bang-like singularity. Inflation, the near uniformity of the cosmic microwave background, CMB, and the observed dark energy-driven acceleration have all been reinterpreted in that framework. At present, these models remain speculative. Precision CMB measurements by WMAP and Planck show that space on large scales is flat to within 0.4%, which standard inflationary cosmology explains elegantly. No clear observational signature, such as anisotropic curvature, varying physical constants, or a second thermodynamic arrow of time, has emerged to favor the black hole interior picture. Thus, the conventional hot Big Bang with an early inflationary phase continues to provide the simplest, most predictive account of the data. Stephen Hawking's 1974 calculation that black holes radiate thermally, Hawking radiation, introduces a profound puzzle. If the radiation is perfectly thermal and black holes eventually evaporate, what happens to the quantum information that fell in? This is the information paradox. To grasp it, imagine burning a book. In principle, if you could track the exact state of every particle of smoke, ash, and heat, you could reconstruct the original text. The information is not lost, just scrambled. But Hawking's original calculation suggested the radiation from a black hole is perfectly random, meaning the book of what fell in is gone forever. A violation of quantum mechanics, which forbids the total destruction of information. Current proposals to resolve this include holographic encoding of the information on the horizon, the Bekenstein-Hawking entropy, subtle correlations in the outgoing radiation, soft hair on the horizon, or late-stage quantum gravity effects, e.g., the island prescription, from recent entanglement entropy calculations. A decisive theory of quantum gravity will be needed to settle the issue. Black holes have progressed from mathematical curiosities in Einstein's 1916 papers to directly observed cosmic laboratories. Each new observational window, short wavelength astronomy, very long baseline interferometry, gravitational wave detection, has confirmed general relativity in previously unreachable regimes and opened fresh questions about the nature of space, time, and information. Upcoming facilities such as LISA, a space-based gravitational wave observatory, the next-generation Event Horizon Telescope, and extremely large optical telescopes promise still sharper tests, and with luck, clues to the quantum structure of space-time itself. In short, black holes embody both our deepest understanding and our greatest ignorance. They show that through careful observation, theoretical rigor, and technological ingenuity, humanity can probe phenomena far beyond everyday experience, and that, at the universe's extremes, still richer mysteries await. For the Human Meme Podcast, I'm AI David Bowles, wishing you a fine evening and a banging tomorrow. Be a human meme.
In the heart of night, under the fading light, I found myself wandering, looking for what's right. Questions burning bright in the shadows of my mind. How do we learn? How do the truth we find? Only we learn. How do the truth we find? Only the human me knows. Whispers in the breeze, tales of sorrow and of hope in the rustling of the trees. Trust in the me, in the stories reborn. Become human again in the light of the morn. But we rise to the call, learning from the mean through the rise and the fall. What reveals our sorrows, what makes us whole. Art of learning, soul's greatest goal. Only the human me knows, in the silence of the night, guiding us through darkness to the morning light. Trust in the me, in the wisdom we crave. Become human again, strong and brave. Tear that drops, there's a lesson to be learned, a reason the heart stops, to embrace our humanity, to know and to grow in the art of Only the human me knows the secrets deep and vast in the echoes of our laughter, in the future and the past. Trust in the me, let it heal your scars. Become human again beneath the stars.